So this is going to be focused on covalent bonds, and more specifically, how do we calculate how much energy in a chemical reaction when reactants going to products, how much energy are we talking about here? So please put on the top of this set of notes, we're talking about covalent bonds. So this is the one place in chemistry. But essentially, you have what we call the reverse of every delta we've done to this point. So what we're looking at is, in a covalent molecule, we have to break bonds in order to make new ones. So we have to look at how much energy is stored in those reactants, and then how much gets reinstalled or re-put into those bonds to make the products. So we are always looking at delta H as being final minus initial. And this is completely different from that. So this is the one place where we don't do final minus initial. And what I'm about to talk about is we have energies for each one of these bonds. And if you go to extra practice worksheet, the last page, you will see this chart that I gave you to use for that set of problems. Or you could look on page 326 in your book. That gives these numbers to you, and they will be provided to you. And again, always refer to this table. This is going to be what I give you on your quiz and your tests for these types of problems. So what we're doing is essentially finding another delta H. So back to thermo, we did delta H many different ways, including Hess's law, including heat of formation. So this is in the same idea of that. Now again, I introduced this pretty early in the chapter just to kind of put it in like a mirror image of what you do with ionics with the Born-Haber cycle. So do realize that this is a little later in the chapter when we've actually drawn some of these molecules. So again, this will not make a lot of sense when you look at the molecules and how I'm drawing them, but it will make a lot more sense later on. So I have this organic reaction of hydrogen plus C2H4 goes to C2H6. This is a pretty, it's called the substitution reaction. It's pretty common in organic chemistry. But what I want you to focus on is this has a double bond between the two carbons. And then over here, you end up with all single bond. So you start out with an alkene and you end up with an alkane. Again, just extra stuff. You don't need to know that. And again, we will be drawing these molecules shortly. So what you do with these types of problems is you find out what is the energy stored in the reactant. So if I look at my hydrogen-hydrogen bond, it's about 436, so that's 436 for that. And then I look at this molecule here. So I have what we call multiple bonds down here. So I have a carbon-carbon double bond, so that's 614. And then I have carbon to hydrogen, but I have 4 of those. So I'm going to have +4. So I look up carbon and hydrogen, and that's about 413. So that is the energy we have in the reactant side. Okay. And then I look at, all right, so I'm going to subtract what's on the product side. So the product side is a carbon to carbon bond. So that carbon to carbon bond is a 348. So that's 348 for the carbon-carbon bond. Plus, I have the carbon to hydrogen bonds, which I've had over here, but I have 6 of them now. So 6, 413, 6 times 413, excuse me. So when I put this all together, this comes out to be 2702. This comes out to be about 2826, excuse me. And I end up with a negative 124 kilojoules of energy. So this is an exothermic process. So in the world of chemistry, that's usually a favored process, meaning the substitution of that double bond to make another, to make it a single bond and add 2 hydrogens is going to probably happen. So see if you could take this reaction. I'm going to draw the molecules for you just because we haven't done them yet. So again, you have 2 hydrogens here, so you got to account for that. Oxygen, we're going to say, is O2. It is on the chart here. We're going to say it's kind of a double bond. We'll talk about that. And then water, you should be able to know what water looks like, but it has an OH bond, but there are 2 of them. So I'm going to pause the video and then show you the answer. So here I read off the chart. I got 1367 from the reactant. Subtracting, again, I have an OH bond. There are 2 of them, plus I have 2 water molecules, so that's why there's another 2 there. So I end up with a negative 485 kilojoules, and that is an exothermic process. So as we get into more of the structures, this will be a little easier to do, but you will always be given a table like this for you to do the math with. But again, that's how we do the calculations having to do with covalent bonds. So now that we have been starting to draw, let's talk about how do we draw these molecules, okay? So this is only for covalent bonds. So again, we are still on covalent bonds. And I only draw covalent bonds doing a Lewis dot structure. So that is all I do. I don't do the same thing with ionics. That's just me. You will see it in the book that they do it both ways. They do some dot structures with ionic bonds. So we are going to draw electrons as dots. Again, we're going to do lines as well. Please know that a line is equal to 2 electrons in the structure. And we're only talking about the valence electrons when we are drawing these structures. So again, the objective is to do the octet rule. And back to the valence electrons, we're talking the s and the p orbitals is really what we're focused on. And because that is our focus, that is where the magic 8 comes from. It is 2 in the s orbital and 6 in the p orbital. So there are some rules with these structures, and then I will show you some weird exceptions. So realize that carbon, nitrogen, oxygen, and fluoride will always follow the octet rule. So they will always have 8 dots around them or 4 lines. Boron and beryllium will have fewer than 8. So boron is only going to make 3 bonds, and beryllium is only going to make 2 bonds. And again, if you look at where it is on the periodic table, beryllium is the second, so it has an S2, and boron has an S2P1. So it makes sense as to why they are what they are. Second row elements never exceed the octet rule, so you will never get anything to go beyond the octet, and we will talk about some things that do. And then the third row elements can exceed the octet rule because of what we call the d orbitals. And again, we did not talk too much about this in first year chemistry, so that is why we're going to spend a little bit more time on this in this section. So when we are talking about drawing some of these molecules, okay, again, going back to the beginning of our notes, we're trying to bring 2 hydrogen atoms close together. So when we draw the electron dot structure, we do 2 dots to up and down to show that we have a single bond. Lines are going to be a lot easier to deal with, but you can do dots. If I look at something like chlorine or any of the halogens, if I have a diatomic molecule of Cl2, I have a single bond between the chlorines, and then I have electrons around it, because chlorine is in the 7th column, so it has 7 valence electrons, so it makes a single bond. So realize that in between, whatever is the bond is called the shared pair. Shared pair, which makes perfect sense. But then the ones that are on the chlorine are called lone pairs. And that's going to come into discussion when we start to do what we call shapes of these molecules, which we talked about in first year. So when we are looking at where things are on the periodic table, so make sure you have a periodic table to kind of go off of here, of where things are located. So I am going to label this as group 1A, and that is going to be my first column on the periodic table. Okay, so we're just going to focus on the first 2 columns and then the last 6. We avoid the transition or the D block in the middle because we're just talking about the valence electron. So this is an S1 that has 1 valence electron. So when I do my Lewis dot structure, I draw the element symbol and then a dot. So something like lithium with a dot is its Lewis structure. So if I go to the second column, that's 2A. That's an S2. I have 2 valence electrons. Again, when I do the dot structures, I try to put the dots on either side. Think of electron repulsion. They try to be as far away as possible. And here's your example of beryllium. It only can make 2 bonds on either side. So I'm going to pause the video and then finish filling out this table. So I completed the table here. You could kind of, stop the video and kind of record it. All I'm trying to do is show you the pattern, excuse me, of the dots or using lines to show what is the Lewis dot structure of that particular element. So before we get into more complicated ones, I try to draw some very simple ones. So I'm going to write, I'm going to show you methane, which is CH4. And again, I don't expect you to know the name. This is just for our purposes. Carbon, of course, has 4 valence electrons. So it's going to make one bond, a single bond around with each hydrogen to make a molecule of methane. Ammonia, you better know ammonia is NH3. Hydrofluoric acid is HF. 2-butene. 2-butene, again, I'm not going to focus too much on organic molecules, but see if you can understand that when we have a double bond, we're going to have only 2 hydrogens being allowed to be there. And then run propyne, that's going to be a triple bond between the first and second carbon, again, prop being 3. Again, I'm not going to have you memorize any of this. I might have you draw it or give you some information on it. But again, some carbon molecules are going to be kind of interesting in terms of some of the chemistry we're going to do. So let's go back to ammonia. Nitrogen has 5 valence electrons. So what you will see is I have a lone pair on it, and then I have hydrogens attached to that nitrogen. Hydrofluoric acid, HF. Don't forget the lone pairs on fluorine. And our favorite, water, has lone pairs on the oxygen and then hydrogens attached. So really, when we first started drawing these first year chemistry, maybe not the organic molecules, but some of them, we just asked you to kind of put them together in such a way to complete their octet. Because again, carbon has a complete octet here, nitrogen has a complete octet, fluorine is happy, oxygen is happy. Hydrogens, again, only want to make one bond. So that is pretty normal for hydrogen. But of course, we have far more complex molecules that we're going to be drawing. So that's going to be in the next video.